All right, so our second talk of the day is by Sam Devlin. So Sam is a senior researcher at Microsoft Research in Cambridge, UK. So I think the UK team is probably the furthest traveling team to get here. So thanks for coming. And he's going to be talking about generalization in RL with selective noise injection. So,
thanks. Okay, so it's been noted recently that reinforcement learning is the only form of machine learning that gets to train on the test set, right? And in particular, that deep reinforcement learning tends to overfit the specific environment that's been trained on. So what I want to present today is a line of work that we've been doing at Microsoft Research Cambridge that led to us achieving state-of-the-art results on OpenAI's coin run environment here, where the agent was able to perform excellently in unseen platformer levels. It's my privilege today to be presenting on behalf of the Project Malmo team, pictured in the bottom right here. None of this would have been achievable without this sort of large interdisciplinary team. So whilst I get to stand here and do the talking thing, this really is a big team effort. The team's probably most well known to the community for open sourcing a platform for enabling reinforcement learning experiments in Minecraft. But we're actually part of a larger game intelligence theme at Cambridge. And so I want to take a moment before I get into the research topic, to talk a little bit about why we're doing this work in video games. Can anybody tell me who this is? I hear some murmurs. Stan Lee, yeah, okay, so the name's coming through. It's actually kind of a trick question. This gentleman was born Stanley Lieber. Stanley Lieber wanted to be a novelist. He wanted to write the next great American novel. But to get by, he took a job writing comic books. And when he made his first comic book, he used the pseudonym Stan Lee because he was embarrassed. He thought that comic books was a waste of time. He thought that this wasn't, his great achievement, the thing that he was going to do. As many of you will know from the murmurs of the name, Stan Lee went on to be a huge success. He was the creative lead for Marvel Comics. He invented Spider-Man, the Incredible Hulk, X-Men, Black Widow, a whole range of superheroes that went on to spin off into all sorts of movies and is a huge success, right? Okay, so why am I raising this at a reinforcement learning day? Well, I think we're in the same place at the moment as a research community in the way that we're using video games. Okay? So this year, ICML, one of our biggest machine learning conferences, was co-located with E3, one of the biggest gaming conventions in the world. I had the great pleasure of attending both. So at E3, there were 60,000 people. All of the event was being streamed to millions of people around the world. And then I went back to ICML, and we had some great workshops on real-world reinforcement learning, one of which was organized by some of the people in the room, so thank you for organizing it. It was great. But one of the messages that kept being echoed was, we need to stop messing around with video games. We need to stop playing games, and we need to get real-world impact. Video games are real-world impact. This is a $100 billion industry enjoyed by 2 billion players worldwide. Why do we dismiss this potential for impact? This is a real-world opportunity to have impact on over 2 billion people worldwide. The demographics have improved considerably. This isn't a medium that's enjoyed by teenagers in their bedrooms alone, right? The demographics are moving ever more towards a 50-50 split between men and women players. The average gamer is now in their 30s, trust me. So I want to just re-emphasize this, and because this is a large personal mission and also something that we work on largely within the game intelligence theme at Cambridge, is that video games is a real case, it's a real world impact, and it's an opportunity for everybody working in this field to have impact within your lifetimes on 2 billion players worldwide, and a way that we can start to make this medium accessible to even more people. So 2 different directions that the team take. One is looking at AI for players. We want to enable entire new types of game genres, right? So we bring even more people into this medium. The example here for why we think of generalization and reinforcement learning is important for this is that a lot of games now, for instance Minecraft, allow players to create user-generated content, right? They can create their own levels, their own worlds, But the AIs in this world tend to either have very simplistic reactive behaviors, or people have to create their levels and their worlds to cater to what the AI is doing. They're being limited by the ability of the AI. If we had AIs that could generalize and be general game-playing AI agents, then players could be free to create whatever worlds that they could imagine. Secondly, we think about AI for the game developers. And so if we want to see this technology transfer into the games industry, we need to make it accessible to game developers. And one of the bottlenecks here is that if you have to retrain your RL algorithm for billions of episodes, hundreds of GPU hours for months on end, that's not going to happen during the dev cycle of a video game, right? Whilst the game is being developed, there's very quick iterations, graphics will change, level design will change, these sorts of things change. And we don't want to have to retrain every single time. We need agents that can generalize and act in new unseen levels based off of training on all the other levels that the team have built before this. So this brings me to the sort of bulk of what the research problem is as far as generalization and reinforcement learning. To give an example of this problem, I want to talk about some work that was done in Cambridge, led by Luke Harris and Sebastian Lee, who were two of our AI residents over the last year. This work was published at the IEEE Conference on Games this summer. The environment is all open source and available there. So what this was, it's a modification of the VizDoom platform to randomly generate mazes. So you can get all these different sorts of mazes created. The agent has to explore the mazes, collecting the red keys, and we can generate lots of different instances, different layouts, different sizes of layouts, different placements of the keys, different textures on the walls. But ultimately, what we want to do is have a training and test split. Okay? So if we take a look at one example, so in the top here, we have one of the mazes, the stars are the keys that they have to collect, and we see in the dashed line the path that the agent has learned to find all of the keys in the space. In the bottom, we have a bunch of deep RL algorithms that we train to do this. All of the lines go up and to the right and do the sorts of things that we expect learning curves to do for these sorts of environments. We'd probably say here, looking at this, that PPO with the LSTM is the best performing, right? It gets up nice and high in the left there. It's low variance. Right. That's probably the one we would select if we were just looking at this example. But then when we take that policy and we put it on a held out test level, the agent performs terribly, right? So we have this new unseen map, different layout of keys, and the agent doesn't know what to do, okay? Because it's overfit to that particular environment, right? So we have the learning curve of the agent here again, and then we have the evaluation on 3 different held out 10 by 10 levels, and if we push it to a 20 by 20 level, it just completely falls apart, right? It doesn't know how to explore these things. What it's learned is a specific path around that specific map, and not how to generalize to new environments. So we refer to this as the generalization gap between the training performance and the test performance. The unintuitive result here was that actually that green line on the far side was the best agent for generalizing. The expectation here is that because it's had more experience during training, that it actually performed better during test time. Okay, so how do we counter this? So we used domain randomization. We trained the agent instead on multiple maps. We generated lots of different maps, trained them on those. We randomized the spawn location, so it sees different levels from different positions. And then we see significant improvements in the performance. So the dark blue, this is a 3 held out test maps. The y-axis is the number of keys they collect in the held out test maps. Dark blue is a random agent. The orange agent is your typical RL agent, just trained on a single map with a single location. If we add in either of these domain randomization techniques alone, we found it didn't perform particularly well, particularly better. But when we use both together, it's a significant improvement. Still lots of room for improvement. In particular, one of the things that's still very challenging on the platform is generalizing to changes in aesthetics. So as I said, we can randomize all the textures that is generated for the different levels, and this particularly causes issues for vision-based RL algorithms. So it's open source. We encourage people to use this for exploring this topic further. Okay, so how else can we approach generalization and reinforcement learning? So we've talked about some of the things that you could do on the environment side, but that's only one half of the sort of reinforcement learning problem, right? We've got the agent as well. So what can we, in the next line of work we thought about, what can we do to the agent to improve its generalization? And so for this, I want to talk about a paper that will probably be published at NeurIPS this winter. This was work led by Max Igel, who was with us on a summer internship. And this is where we get our coin run results. And in particular, Max wanted to look at how to apply regularization methods from supervised learning onto the reinforcement learning case. So regularization is regularly used in that context to improve generalization, but it was developed for supervised learning, and the RL case is different. So we wanted to think about what are some of the key differences between reinforcement learning and supervised learning that show how we should modify regularization for this context. So one of the first issues that we note is that reinforcement learning agents act in the low data regime early on in training, right? So the first time they see a map, they haven't got much experience. For this, we used this mini-grid environment that's open source again on GitHub. It's a simple grid world. We base it off of vision, so each grid is a dot in a 2D image, and the agent has to get to the green dot. The slight difference here is that every single time that the agent completes the level, there will be a new maze, a new map to get through. And there's a timeout. So if the agent doesn't get to the goal, then end of episode, new maze, new instance. If we just set off a deep RL algorithm on this without regularization, we find the agent doesn't do very well, right? This is, to think of this intuitively, this might look like it hasn't really trained, but if you think about it, this is an entirely new environment. It's never been there before, and it's timing out. So it's not reaching the goal. It's not, it's never actually seeing the reward, so it doesn't know how to act. What we need is a form of regularization that allows the agent to learn very quickly good features. And so what we propose in the paper is to use a variational information bottleneck on the policy. So this introduces two losses, one to minimize the mutual information between the state's input and a latent variable that we introduced, Z. And then the second one is to maximize the mutual information between the actions and the output, so the latent state Z again. This may be similar to those familiar with sort of variational autoencoders. The difference here being that instead of a reconstruction loss, trying to reconstruct the image, we actually focus on maximizing mutual information for the downstream task. Right? So what are the actions that are going to maximize reward? We again use this mini-grid environment, and we see huge performances. So the dark blue and the light blue are the two agents that are using this form of regularization. The orange and green, the orange and red are using other forms, and the green is the performance of the agent that has no regularization. Qualitatively, we see a much more improved policy. So this is, again, this agent was never seen this environment when it was trained. Right? This is the first time that it's ever seeing it, and it manages to move towards the goal. Okay, it's been trained on entirely different ones and then put into entirely new environments. Again, if we try to quantify this a bit more, what we see is some gain in single room mazes, but in the 2 and 3 room mazes, again, that's where there's a real gain, where it's actually able to solve some of the 2 and 3 room mazes, whereas the other methods can't at all. One intuitive way to think about this is that it's trying to compress features, right? It's trying to learn the simplest features. So instead of, in the previous setting, the agent's learning a specific path, like it's learning every road that it walks down. So some of you locals might have used every local bit of knowledge you knew to get here, right? Walk down that street that you know, past that deli that you know. But for the rest of us, the way we generalize to a new city is that we think, I know how to read a map, I know how to read street signs, or in a city like this, I can just follow the grid system, right, and I'll go north as many blocks as I need to, and then east, right? So thinking we want to get that simplest possible policy that's going to get the results. Okay. Second issue, RL agents generate their own data set. Okay, if we add stochastic noise as a form of regularization into our agent, it does dumb things, right? So what we have on the left is an agent with batch norm that is just applying this regularization everywhere. And it's mostly learned how to do this environment at this point, but it walks straight into the saw at the last minute before the reward. So the fact that we're adding in random actions to our policy means that we're getting suboptimal data back, right? We're reducing the rewards we see. We're prematurely ending episodes. So we're actually damaging the data set that we're collecting. And so here we see, this was the previous state of the art on this environment. And we see a very large generalization gap, so we saw that this was an opportunity to improve on. And so the idea here is to use selective noise injection. So instead of adding noise injection to every element that we could in the value function in our policy, we just add it to the policy that we're learning. So we, again, try and get the simplest policy possible, but we don't add it to our rollout policy. So we're not affecting the data that we're collecting for the agent. The agent still is acting as best it can when it's collecting data, but we've regularized the policy that we're learning instead. And in doing so, we found that we got state-of-the-art performance. So our bars go higher and to the right, both on the training set, which is the top lines, and then in the test set, where we've shrunk that gap, the generalization gap in doing so. Okay. So to conclude there on the work that we've done on generalization, there's 3 different approaches that we've talked about as far as how to improve generalization of the reinforcement learning agent. The first being on the environment side, the fact that we can use domain randomization. So this was the Vizdoom examples of randomizing the maps, randomizing the spawn locations. And then 2 other ideas that came in more on the agent side. And so our recommendation there is that if you're using stochastic noise injection as a form of regularization for your agent, that you do it just on the rollout policy, not on the, you just do it on the policy that you're learning, not on the rollout policy. And we found in particular that this variational information bottleneck was a very good form of regularization for deep reinforcement learning and generalization settings. Yeah. With the time remaining, I just want to talk a little bit about future work and the things that we're going to go on to look at. And in particular, one of the things that we're really focused on is generalization in multi-agent learning. So we ran this competition last year in Minecraft. We had a set of multi-agent tasks. Again, these are all open source and freely available. The first was 2 agents having to collaborate in essentially a sort of predator-prey scenario where they have to capture this pig. But the generalization test in the competition we ran was that we'd set out 5 particular instances of the environment, but then when the agents were submitted, we tested them on 5 different instances. So the weather conditions might change, the form of mob that you're trying to capture might change, and so forth. Layouts, mazes, again, to do. We also set 2 more tasks. One is this treasure hunt, where you have heterogeneous roles in that one agent can collect treasure and take it to the exit, but it can't defend itself. The other agent can attack and defend from the skeleton that's in the environment, but it can't collect the treasure. Again, it's a collaborative environment. The team only get rewarded if that one agent survives to get the treasure to the goal. The final one was a build battle. So this is a game that people play within Minecraft where you see a structure in one area and then you have to recreate it as quickly as possible in another space. And so they need to collaborate to build that structure, recreate that structure in the other space. We had a number of good entries to this competition, but they all only succeeded in playing well together, right? The agents that people trained played well with other agents that were trained in the same way, right? So if we instead match them up with any other agents that were submitted to the competition, performance drops remarkably, right? They've learned policies that are very tightly correlated with the other policies that they've trained with. This is a result that's been shown a number of times now, to the extreme that even if you retrain with a different random seed, then those agents will typically not play well with another agent trained with exactly the same method, same hyperparameters, but a different random seed. And so what we want to work on is generalization to agents that you haven't seen before, right? So how do you do ad hoc teamwork, right? If I was to play this game with anyone in the room, I'm pretty sure I could quickly adapt and play these games with anybody here, right? But the agent can't do that. And so we want to be able to do that quick adaptation. And ultimately, that is to link it back to our goal of trying to get this into the hands of players, right? So players are other agents that are going to learn and adapt online, right? But you can't spend billions of steps, hundreds of GPU hours training with every new player, right? They're going to get bored and play the next game instead, right? So we need to be able to generalize to new players, and we need to be able to do quickly online so that we can reach out to, again, bring in other people into these games, create collaborative agents that can play and help people succeed in these new environments. Okay? We've taken a couple of different angles on this. In particular, we're looking at meta-learning, and if you want to speak to Katya about that during the day, or exploration, and my colleague Camille here, if you're interested in that sort of angle, recommend speaking to those. Or if you want to talk more sort of about multi-agent learning, then please do feel free to reach out throughout the day. That's everything I had. Thank you.
So we have a few minutes for questions.
Everyone wants coffee.
Yes.
I'm jet lagged. I've got the excuse.
Until questions, no coffee. Thank you.
Very good talk. I just wanted to ask a little question about the noise injection.
Yep.
So you would do the rollout with the optimal learn policy, and then when you're doing the update, you would add some noise in what that is. So does that affect exploration in any way then? Because you're still kind of could end up in like a suboptimal location if that's what you had learned, even though you're adding the noise during the update, you don't actually have the reward information for what. I'm sorry, my question's not super concise.
Well, but then your data set, you still have, so you do have the reward information because you've still got the state action reward from the rollout policy, right? So you still have that to do the update with. The adding the noise at that stage is what then gives you the regularization, right? So the other side was about how it affects exploration. So the fact that you're trying to learn generalizable policy and you're adding noise to the learn policy that we then take a deterministic version of to do the rollout in means that you are getting different exploration there, but you're at least still acting optimally compared to the policy that you've learned, right? Rather than adding it in the rollout policy where you're going to take suboptimal actions and end the episode prematurely.
Thank you.
We have time for one quick question, if there's any. Okay, well then go and... Oh, did you have a question? Okay.
This is perhaps not a very good question, but it strikes me when you're trying to do collaborative work that there's some notion of intent or goal when you're trying to collaborate with other agents. And do you see that manifest in some way in the types of representations that you're developing and the policies that you're making? Those things allow you to switch from doing things one way or another way, especially if you're transferring to work with another set of team members. Is that something that's important in what you're doing?
Yeah, absolutely. And I think for that sort of ad hoc teamwork setting, having this sort of theory of mind to reason over what is the goal that they're trying to achieve, I think that's really important. In fact, Roberta, who's over here from NYU, did an internship with us before that was looking at this sort of idea of learning, trying to figure out what particular goal or route people were taking and whether that was actually being encoded in the latent space of the agent. So I recommend talking to Roberta about that.
Okay. Thanks again, Sam.